All right, so let's work a few of these problems. There are a lot of them, have an answer sitting there for us. So I'll work a few of them that don't have the answers sitting there. But if you can't solve these, then certainly jump into the Google Meet and have us help. I was looking at grades on those review quizzes that had everything but gas stoichiometry on them. And a lot of us got over 100% on those. Excellent job there. But there are a few of us that are still struggling on these good bit. I would go back and look at some of those older quizzes where you were actually working problems. The answers are available to you now, so you should absolutely rework those problems. And if you can't get the right answers, you should get a hold of us and try and get some help on that. Anyway, let's go ahead and look at question number 3 here. What is the final volume of a 400 milliliter sample of gas? So we've got a volume here that is subject to a temperature change and a pressure change. So I have all 3 things changing here, right? I have volume. They're asking about volume changes. We see temperature changes, and we see pressure changes. So as we're going through, we want to make sure we're figuring out which things are changing. So I'm going to go ahead and make my list. My initial pressure is 760 millimeters of mercury. My new pressure is 360 millimeters of mercury. My initial temperature is 22 degrees Celsius. I'm going to go ahead and change that as I write it down because I know that's no good. I don't want Celsius. I want Kelvin. So that's 295 Kelvin. My temperature 2 is 30 degrees Celsius. So I'm just going to go ahead and write that down as 303 Kelvin, right? 273 plus 30 will give us 303. My initial volume is 400. Now, be careful because we don't always say, initial and then final. You want to make sure you're pairing things correctly. But with all of these, they said, what is the final volume of this when it went from this to this, from this to this, right? So then we have our equation. P1 V1 over T1 equals P2 V2 over T2. Right? It helps to write out that equation. Then we go ahead and double check our units. Everybody's going to cancel. My final volume is going to be in milliliters. So 760 millimeters of mercury times V1, 400 milliliters. See, that's why that helps. There's all these numbers over here. And as I was doing it, I had to double check back where the number, right? It helps to make that list, 295 Kelvin. So P1, V1 over T1 equals P2, 360 millimeters of mercury times V2, that's the thing I'm looking for, divided by T2. From here, it's a cross multiply and divide kind of thing. I'm going to cross multiply by the 3 things and divide by the things that are attached to V2, right? So I'm going to do 760 times 400 times 303 divided by 295 divided by 360, right? You can do that in a bunch of steps if you want. I think the simplest way is to just do the cross multiply and divide, right? Do your cross and then divide by the things that are attached to the V2. So 760 times 400 times 303 divided by 360 and divided by 295. And that gives us an answer. I don't know how well you can see that on there. Maybe if I hit the lamp on there. Yeah, you can see a little better. That gives us 867. Looks like we've got 4 sig figs, 3 sig figs on all of these. We've only got 2 sig figs there. So let's go ahead and round it to 870 millimeters, or no, not millimeters, milliliters, 870 milliliters, because we've only got 2 sig figs right here because there's no decimal point. 2 sig figs right here because there's no decimal point. Right? Okay, let's see. This is a PivNert problem. PivNert problems can be kind of tough, so let's go ahead and do a PivNert problem. I have an unknown quantity. When we say quantity in chemistry, amount, we're usually talking moles. Sometimes grams, but usually we're talking moles. We've got a temperature in a container with a volume and a pressure. How many moles is that? So pressure is 560 atmospheres. Remember here, it didn't matter that we weren't in atmospheres because they were going to cancel. Because of that R, in our PivNert problems, we're going to have to recognize that our units need to be in atmospheres, right? So 560 atmospheres, a volume of 25 liters, a number of moles is what we're solving for. R is 0.08206 liters atmospheres per mole Kelvin. and a temperature of 1195 Kelvin. So my equation is PV equals nRT. You can plug in and then rearrange, or rearrange and then plug in. I rearrange first because I'm lazy and I don't like to write these a bunch of times. So I'm going to divide by R and T, right? Because that cancels those out, now ends by itself. So pressure, 560 atmospheres, times volume of 25 liters, divided by 0.08206 liters atmospheres per mole Kelvin, times 1195 Kelvin, right? So 560 times 25 divided by 0.08206 divided by 1195, and that's going to give us 142.7. So it looks like I was actually a little sloppy when I made this and left 3 sig figs here, which really we only have 2 here and 2 here. So we really should round it to 140 is a better answer on there if we're thinking in terms of sig fig stuff. Right. We haven't written the test for Friday yet. I don't plan on, being a sig fig hawk on that and stuff, but it's still good to keep that in mind. Okay. Let's see. Effusion. Yeah, I see an effusion problems, and those have been giving us a little bit of trouble. So let's do one of those. Under the same conditions of temperature and pressure, how many times faster will hydrogen effuse than carbon dioxide? So hydrogen and carbon dioxide. Carbon dioxide is CO2. Now, we've got to be careful. So many of our gases are diatomic, right? So I want to make sure and list that as H2. H2, O2, N2, Cl2, Br2, I2, F2, right? Those Hunkelbriefs, they're on the back of your periodic chart. Maybe just make a list of those guys before you start working problems so you remember those. So let's see. So how many times faster is hydrogen than carbon dioxide? So that means I'll go ahead and make my list here. Molar mass of H2 is just 2.02 grams per mole. Carbon dioxide is 44.01 grams per mole. You probably have that memorized just from working stoichiometry problems. The rate of hydrogen and the rate of CO2. And this is one of those that'll bother a lot of students because they're like, well, they didn't give us any rates. They said how many times faster. So just make the rate of CO2 1, right? That way when you get your answer for hydrogen, that's how many times faster it is. So remember, this is the inverse, like flippity floppity one, right? So we'll do the molar mass of CO2 on top, molar mass of H2 on bottom, then we'll have rate of H2 on top over rate of CO2. And we put the CO2 in as 1. So we'll do the square root of 44.01 divided by 2.02 equals 1 over that, right? So it's just, all I have to do is 44.01 divided by 2.02, square root that mass, and that's going to give us 4.67 times, right? 4.67 times faster. I put the X, I guess I was saying times faster. Maybe I'll write the word so I don't confuse anybody. 4.67 times faster. Right. Okay. Let's look at, here's a Dalton's law of partial pressures problem. Maybe we'll work one of those. If we have a mixture of gases, right? So note, when I start hearing mixtures of gases or collected over water, those are some keys to tell me Dalton's law of partial pressures. Mixture of gases, that's 3.1 moles of helium, 2 moles of hydrogen, 4.5 moles of CO2. What's the partial pressure of each gas if the total pressure is 3? Well, if the gas is 50-50, right, then half the pressure comes from one, half the pressure comes from the other. If it's 33, 33, 33, then a third and a third and a third, right? So here we just don't have those ratios. So I just need to figure out basically what percentage is each gas, and it's going to have the same percentage of total pressure, right? Let me say that again. Whatever percent count you are, you're going to be the same percent pressure. So if you're 100% of the count, you're 100% of the pressure. If you're 30% of the count, you're 30% of the pressure. So if we do 3.1 plus 2.0 plus 4.5, that's going to give us 9.6 total moles, right? So if we do 3.1, this is for helium, 3.1 over 9.6, 3.1 divided by 9.6. Let me actually type that into my calculator correctly. That gives us 0.3229. Going to keep an extra digit at least. So that's the fraction that we are. So 32% basically, right? And then I'll multiply that by 3.23 atmospheres to get my pressure of that one, times 3.23 atmospheres. So that is 1.04 atmospheres of pressure is coming from our helium. I'll do the same thing for the other two, 2.0 over 9.6 and 4.5 over 9.6, right? If we did this conceptually, if we said who gave us the most, who gave us the least, right? You'd be able to do that, no problem. This first step can just be a little confusing for some folks. So then 2 divided by 9.6 gives us 0.208. Again, times it by the total pressure. The count ratio is the same as the pressure ratio, right? That's another way you could think about this, right? There's a lot of ways we could solve this one, but we just have to be able to figure out a way to address the issue and move forward. But masses don't matter and stuff. What matters with gases is counts, because the bigger ones just move slower. Divided by 9.6 times 3.23. So this was 46% was this. So that means 46% of the pressure is going to come from that one, 1.51. Now, if I add these three up, if we do, can you see that on there? So if I do 1.5 plus 0.468 plus, oh, wait a minute, not 0.468, 0.67 plus 1.04. I was looking at my calculator instead of looking on the paper, right? 1.04 plus 0.67 plus 1.5 will give us 3.22, right? So 3.23, same thing with rounding stuff, right? Okay, what are we at? 11 minutes? All right, I better stop or YouTube's going to boot me off.